Thank you very much. We are even ahead of schedule. Wonderful. I feel very privileged to have a chance to participate in this meeting. And I think I owe this privilege of speaking, to a quote. And this quote is the opening quote of the book written by Norbert Wiener in 1948. The book is called Cybernetics. And obviously, from the quote, Norbert Wiener had great ambitions about cybernetics. He wanted to create a new field. And he wanted to ground that field in a noblest heritage. And what is noblest than combining the Greek, the Latin, and Maxwell? That's exactly what he did. So he came up with this Greek translation of governor, and the result was cybernetics. And he said this is a way to acknowledge that Maxwell should be considered as the father of the field, as the father of what we would nowadays call control theory. I say that I probably owe the privilege of speaking at this meeting to Norbert Wiener because, well, first of all, you should know that if you read the press in the late 40s, then you realize that the cybernetics launched a sort of a craze that is very similar to the craze that we live in the age of ChatGPT. So the titles of the newspaper are extremely similar to the titles of today's newspaper. Machines that think, this is 1950. Mechanical slaves forecast, devaluing brains in industry. I think we could read many of those titles today. Now, most of what I will tell you about the history of Maxwell and the origins of cybernetics is due to the historian Otto Meyer, who wrote several papers about digging into the work of Maxwell, the origins of cybernetics. And yeah, he started his article with the quote of Norbert Wiener. And then he says very gently that indeed, until 1948, Maxwell's paper on governors was almost entirely ignored. And so he comes up with an explanation of why this paper was ignored, and I will tell you a little bit about that. So I will divide my presentation in three parts. I will tell you a little bit about what is in Maxwell's paper on governors, and what is the relationship of this paper to control theory. And then I will tell you a little bit about cybernetics, because actually Cambridge has such a central place in the history of cybernetics that I think it's worth connecting cybernetics to Maxwell's. And then you could think that this story stops in 1948, but I will not resist talking about my research field a little bit, which is neuromorphics. And I put it in the future because I think it's still to happen. But to a great extent, I just think of neuromorphics as a renaissance of cybernetics. And so in that way, I think I'm doing justice to the heritage of Maxwell's papers that goes straight to this very day. Now, Maxwell's paper, the origin of Maxwell's paper is what we call the What's Governor. And here you have to go 1 century back from Maxwell's time. So late 18th century, the beginning of the steam engine and the invention of this ancestor of the cruise control system that you have in your car to regulate the speed. So this was probably invented by Huygens, even before Watt, but Watt took this device to solve a very important problem, which was to make the speed of the engine somewhat independent of the load of the engine. So this is sort of the modern version of the What's Governor. It's a Lego What's Governor that that I used to show to the students in this very lecture room. And that is a very nice way. I would use this in the very first class of the control course, because it's a nice way to illustrate at the same time how basic and simple is the concept of feedback, and at the same time why you need a theory of feedback. Sorry about this. So how does the Watt governor work? Well, due to the speed, you have a centrifugal force, and so if the speed increases, the fly ball will open and will close the inflow of the steam. Therefore, the speed will go down. And conversely, if the speed goes down, then the fly balls will come down and will open the valve, and you will have more steam. So you see that you have added a mechanism to the machine that you want to regulate, and this mechanism is sort of applying a force that is proportional to the regulation error, to the error between the desired velocity and the velocity, the actual velocity that is varying because of the variation of the load. Okay, so this is this very simple principle of using feedback, and we call it negative feedback, because if you would draw this in a block diagram, you measure the speed and you inject at the input, so inject a force that is proportional to the reference minus the speed. So it's negative feedback. And of course, negative feedback is the essence of homeostasis. Okay. So a very simple principle, but in fact that occupied a lot of the engineers from the times of Watt up to the time of Maxwell, because it's actually quite difficult to tune this mechanism. If you make the mechanical link too stiff, then typically you get instability, you get oscillations, and so you get the problem of what we call high gain feedback. But on the other hand, if the connection is too weak, then you get a very sluggish regulation. And therefore, it's a trade-off. How strong should be the connection between the controller and the system that you control? And that's why you need a theory. That's why we explain to students that if you want to design good control systems, you need to learn how to balance this trade-off. And indeed, during the 18th century and 19th century, you had a zoo of such speed regulation devices that were developed. I will talk a little bit more about the device by Jenkins, which is here. It's the first time that I see it, the real device. And indeed, we also have another paper by the same Otto Meyer, who has been studying this importance of speed regulation throughout the 19th century and the interest of physicists for this technological issue that you could consider very trivial or basic. And so in the introduction of this paper, Otto Meyer highlights the fact that big names in physics, including Harry, Foucault, Kelvin, Maxwell, and Gibbs, paid attention to this problem and how to tune this regulation mechanism. Now, the reason we have heard earlier today, the reason was that actually physicists needed speed regulation. We have heard several times today that a big problem was at the time was to measure resistance, to measure the resistance of a coil, and that an experiment had been devised, one of these devices developed by Charles Jenkins, to measure the resistance of a coil by spinning, by rotating this at constant speed, and then the device would incline due to the gravitational fields, and the angle would be proportional to the resistance, provided that you had a very good measure of the velocity. So it was critical to get a reliable measure of the resistance to have a reliable velocity and to regulate this velocity very accurately. So this is the device. In other talks, I would have needed a picture, but you have seen the device itself. And you see that it's slightly different from Watt's governor. It also looks more complicated, actually, than the Watt's governor. So we are going to come back about the difference between Watt's governor and Jenkins' governor. Okay, so what is the contribution of the paper that Maxwell wrote on governors? essentially two principles that we still teach to this date as in the first control course. The first one is that in order to analyze this instability mechanism, you have to study the stability of a mechanical system or a dynamical system, and that you can do that through the principle of linearization. And then the second thing, which is also a very important lecture in the beginning of the control course, which is the difference between what we call proportional and integral control. And it's remarkable to see that those two principles were first put forward in this very paper, which therefore deserves to be called the first paper of control theory. Now, Fuller is also another historian who wrote several papers about these speed regulators, and he's not very kind to Maxwell's paper on governor. He said it was probably written in a forced attempt to free his mind from control problems. For this reason, no doubt the paper lacks the patient lucidity which Maxwell was capable of. It is written in a terse and inconsecutive style, and some of his descriptions of governors are too enigmatic to be readily comprehensible. The material in the preceding section of the present paper will, it is hoped, clarify this aspect of Maxwell's paper. So, indeed, the paper itself is, you can see from the paper that Maxwell was not particularly interested in the detail of the calculations, but still, I think it's remarkable that, in fact, you could say the same thing about many papers written in control. So in that sense, it's also a control paper. But clearly, he was interested in the principles that engineers should be using to study the analysis and the design of those devices. And he was very right in identifying two key principles that are still taught today. So the first thing is to observe that it is all about stability analysis of an equilibrium, and that if you want to understand the stability of an equilibrium, you can confine yourself to small deviation. Therefore, you should linearize the motion around a specific equilibrium. And then, of course, he was not starting that from scratch. He was using his own work, and we are going to hear his earlier work on stability theory later today. So he was just reusing something he knew very well, how to analyze the stability of a dynamical system, and saying, look, engineers, this is the theory you need to apply if you want to analyze and understand how the limitations of this device. Interestingly, this is the sort of a preview of the talk that we will hear in the last session on the stability of Saturn rings. Maxwell had won the Adams Prize for that work 10 years earlier, and so he was just reusing that applying that theory to the governor. Interestingly, one of these main conclusions of his talk is that of his paper is that once you analyze the stability of the linearized system, you can determine stability by checking that the roots of a polynomial have all negative real parts. And so this is stated very explicitly in that paper in a slightly different terminology that we use today. So all the possible roots, all the possible parts of the impossible roots. It's such a poetic way of what we say today, all the real parts of the complex roots of a polynomial. But modulo this change of terminology, this is exactly what we teach. And the fact that now the question is, how can you determine that all the roots of a polynomial are in the left half plane, have negative real part, without computing the roots? And Maxwell didn't know how to do that. He said that in the paper, I've not been able to completely determine those conditions for equations of a higher degree than the third, but I hope that the subject will obtain the attention of mathematicians. And indeed, Ruth, we also heard of Ruth this morning, later on provided a general solution of the problem, citing Maxwell's paper and getting the same Adams Prize for this result. By the way, it might be thanks to Ruth that we know of Maxwell's paper on governors, because Ruth's criterion to check that the roots of a polynomial are in the left half plane it is something that we still teach today. It is something that Norbert Wiener knew about, And it probably shows the culture of Norbert Wiener to have gone to the paper and who have traced the origin of that result back to Maxwell. So Maxwell-Roots connection, we heard a little bit about that earlier today. Both graduated from Pelhřimov in 1854, Root as a senior wrangler, Maxwell with the second place. They shared the 1854 Smith Prize. Maxwell won the 1857 Adams Prize for the memoir on stability of Saturn rings that we will hear more about later. And Root won the prize 20 years later for his solution of checking that the roots of a polynomial have real parts. So a very nice history of the early days of control theory. Now there is a second aspect in this paper, which is this distinction between proportional and integral control. And that was known at the time, but still Maxwell was the first to sort of try to formalize the theory of proportional versus integral control. This is from the text of Maxwell. It's not very clear. This is how Fuller explains it in his paper. And here it's pretty clear that in the first case, which would describe what people call not a governor, but a moderator. So in fact, the name what's governor is incorrect. It should be called a what's moderator. In that case, the force that you exert to correct the velocity is proportional to the velocity error. And you can show that when the force is proportional, you never get a zero error. You always have a residual error. Instead, in integral control, you add a second device on top of it, and you make the acceleration. So this is the purpose of the second plateau here that is separated from this device. They are only connected by friction. And this second plateau, if you neglect friction, has a force that is exactly proportional to the velocity error. And clearly, if this system that is combined, so y would describe the position of the plateau, x would describe the position of the cylinder, and if this system reaches equilibrium, clearly you see from the first equation that the only way for the plateau to reach equilibrium is the velocity of the cylinder to be equal to the velocity of the desired velocity. So this is a device that is more complex, that has a force that is proportional to the integral of the error. And the big benefit of adding such a force to the proportional control is that you ensure the exact steady-state regulation. And this is one of the main outcomes of the first control course, of the first theory of control systems design, is to make the students aware that if you want to achieve exact regulation, you need integral action in the controller. And it is said that 99% of the control systems that are out there in the industry only have proportional and integral control, and that integral control is the very reason why control is so massively deployed. So you see that it went a long way and was sort of for the first time studied theoretically in this paper, and actually it was not solved. So this is the difference in the device, the proportional action of the Watts moderator and the integral action of the Jenkins governor. So this is a governor, okay? Now, it was actually not clear at the time whether this integral control term was compatible with the stability of the closed loop system. And actually, Maxwell didn't really resolve that because he would have had to determine the roots of a fifth-order polynomial, something that he could not do. But he sort of actually still said that stability will be the consequence of this criterion. So even if he did not verify, he showed how to verify stability. And it's something that is not very intuitive for the students, the fact that if you have a term in the controller that is proportional to the integral of the error, nevertheless, you can have closed loop stability in the control system. Okay, so the second fundamental contribution of Maxwell's paper. So Maxwell's paper really planted the theory of control system by bringing the attention that this is just stability theory of dynamical system on the one hand, and by emphasizing the difference between proportional and integral control. Back to cybernetics. Why did Wiener want to root cybernetics in Maxwell's work? Well, cybernetics, Wiener was at MIT in the US, but there was a lot of the cybernetics developed in this very place. And when I joined my college, Sydney, Sussex, one of the first things that I learned is that a famous alumni of the college was actually the British father of cybernetics, who is William Ross Ashby. And so Ashby, I got interested. I didn't know about Ashby before that, but I got interested in his work, and I found it quite fascinating. First of all, he was not an engineer. He was a psychiatrist. And most of the roots of cybernetics in England are actually from the very first attempts to try to think of the brain as a machine and to try to think about the analogy between the regulation of the brain of an animal and the regulation of a machine. So remember the definition of cybernetics of Norbert Wiener, a common language to talk about control and communication, whether in animals or in machines. That was really the entire vision of cybernetics, to have a common language to study what you would call artificial intelligence nowadays and natural intelligence. And you see that Ross Ashby wrote 2 books on cybernetics, one called The Design for a Brain and the other one, An Introduction to Cybernetics. And psychiatrists and engineers together create this famous ratio club in Cambridge. And Ross Ashby was one of the founding members of the ratio club. And this is his account of the first meeting. We have formed a cybernetics group for discussion, no professors, and only young people allowed in. How I got in, I don't know, unless my juvenile appearances. He was probably in his early 40s when he joined the ratio club. This is a famous picture of the ratio club, and you recognize many of the big names of the 20th century in Cambridge. Donald Mackay, John Westcott, who was the first control chair at Imperial, Ashby, Horace Barlow, that I will mention later, and Alan Turing himself were all members of this club that didn't survive very long. They met about 30 times between 1948 and the early 50s. I'll come back to that. And they were studying sort of very simple machines. So one of the most famous cybernetics machine is the Walters tortoise on the left, which is just the ancestor of the Roomba vacuum cleaner that many of you might have in their rooms. And I like to show this because I still find it quite striking that the one machine that has made into most households today is a machine that was conceived in the very early days of cybernetics. Now, what were the questions behind these machines? The question was that the control of a machine and the control of a brain involve 2 aspects. One aspect I already mentioned when talking about the speed regulation is the homeostasis, the regulation, making the machine robust to external disturbance. But of course, the other aspect of an intelligent machine is the ability to make decisions and to switch between different types of motions. So the vision of cybernetics was really to design machines that had a number of discrete states, the states of what we would nowadays call an automaton, but that each state of this automaton had to be regulated with homeostasis. And the big challenge was, how do animals combine those 2 aspects of control? Well, I would say that the one device that symbolizes cybernetics in the same way as the governor symbolizes the work of Maxwell is the mixed feedback amplifier. The amplifier, so the design in 1948 was no longer mechanical. It was now a circuit design. And the fundamental element of the circuit design was the operational amplifier. And the amplifier, you see that you can take the output of the amplifier and wire it to the input. This is how you create feedback. And you can wire the output of the amplifier either to the negative port of the amplifier or to the positive port of the amplifier. In one case, you apply positive feedback, so you make the feedback loop proportional to the negative error. In the other case, you do negative feedback. So mixed feedback, the great challenge of cybernetics was to acknowledge the difference between positive feedback and negative feedback. Whereas Maxwell had only studied negative feedback, the corrective feedback, the homeostatic part of feedback. What is quite fascinating is that when the amplifier was invented early in the 20th century, only positive feedback was used. Why? Because those amplifiers with positive feedback were the switching elements of the circuits. They were the ancestors of the transistors. And it's much later that engineers realized the benefit of also connecting to the negative port and to also exploiting the regulatory properties of the amplifier. Now, what is fascinating about the device of the cybernetics age is that with one single device, by changing the relative weight of these two feedback loops, you sweep between two worlds. You sweep between the world of analog regulation, where you make the design insensitive to disturbances, and the world of positive feedback, where you make the design a switching device that makes discrete decisions. Why is this very important? Because very soon after the publication of the books of cybernetics, it was the end of cybernetics. Why was it the end of cybernetics? Because of the first computer. And in just 2 or 3 years' time, the whole scientific world switched from continuous to discrete. Not only in engineering, but at the same time also, of course, in biology. This is also 1952, the discovery of DNA, and the whole world of biology switched from continuous physiology to discrete molecular biology. It's really a very fundamental shift in the 20th century, both in science and engineering, a switch from the analog continuous physical world to the discrete world of computation. So that was the end of the cybernetics age, because when Shannon published his paper, actually the same year as the Book of Wiener, they were colleagues, they were in the same corridor. Shannon essentially said, that's not the way forward. The way forward is to separate positive feedback and negative feedback. In fact, the way forward is to make positive feedback obsolete by the computer, which is a purely discrete machine, and then to design feedback loops only for the regulatory properties. And since that time, the only thing that we teach to students is negative feedback, Maxwell. Okay? But we have made positive feedback obsolete because from that point on, it was sort of resolved by the computer. What is the price that we have paid for that? This is what we are living today. We have created a big, big wall between those two worlds. We have completely separated the regulation of a machine and the automation of a machine. And in fact, most control engineers spend their time today to try to reconcile, to connect the computer to the physical machine. And all the bottlenecks of artificial intelligence are in this wall that we have created, and that doesn't exist in the animal world. Because if you look at an animal, how do you distinguish what is regulation and what is automation? So the big success of the digital technology has also been a very abrupt end to the cybernetics dream. But that's not the end of the story. We can talk a little bit about the future. I have, 5 minutes left? More. Plenty of time. Good. So then I can talk a little bit about neuromorphics and why neuromorphics is just a renaissance of cybernetics. Where does neuromorphics come from? It comes from this paper that was published in 1990 by Carver Mead, a physicist from Caltech, he had spent the first half of his career in the golden age of CMOS technology. Okay, so he was, at the forefront of digitalizing the world, and he became obsessed by the inefficiency of computer machines with respect to animal brains. And he started asking, why? why is computer technology so energy inefficient? Of course, most people in 1990 considered him as a lunatic. In 1990, digital technology was a synonym of free technology. It cost nothing to send an email over the ocean instead of sending a letter. It cost nothing to communicate over the internet. That was a time where I was a student. It was a time of free energy for information engineering. And Carver Mead made a very radical proposal. He became convinced that the advantage of the animal world, what makes the animal world able to be so energy efficient, is that instead of using bits that are clocked as in a computer, as the medium of information, they use spikes, action potential, events. And they don't use a clock, they use rhythm. And he became persuaded that, in fact, it would be perfectly possible to use the computer. He didn't want to crash his own machine, but it was very possible to use that same machine, to use it completely differently, but instead of the transistor switching between zeros and one, transistor having very small transition and transistor spiking instead of switching. 1990, today, it has been a niche until 2015. In 2015, there was the first neuromorphic revolution. It was the commercialization of the first event camera. And 2 years later, Intel launched his first neuromorphic computing chip that is a way of computing in a computer with spikes as opposed to bits. But let me briefly talk about this event camera. That made a very nice article in The Economist just a couple of years ago, and that is now becoming a real revolution in computer vision, but just in the very last 2 years. What is the link with cybernetics? The link is that the dream of the neuromorphic camera, of the event camera, is to get the best of the two worlds, is to reconcile physics and algorithmics, is to reconcile the discrete world of computer science and the continuous world of physics. And this is illustrated by the fact that the analog camera is, of course, a heritage of the analog world, the ancient world, that only the expert love because the quality of the images is continuous, but that is unreliable, that is very fragile. The digital camera is way more reliable, but it's hugely inefficient. Even if it costs nothing to store an image, when you have to store 20 images per second, and when you record just a black scene for the whole night, it's extremely inefficient. Instead, an event camera has, each pixel has an analog detector, and when it detects a change of intensity, it spikes. So the output of the camera is not a stream of images, it is a cloud of blinking dots. And if nothing happens, nothing is recorded. Why is there so much hope in making the event camera the best of the two worlds? Because the signal is analog, it's physical. And you could say that you have a lot of information in the timing that separates the spike. But at the same time, you can always count the spikes. So this is a very special type of analog signals that has the reliability of computers of discrete technology because you can count the spikes. Why am I telling you that? Because this story is incredibly close to the story of Maxwell. And I will finish my talk by showing you briefly two things. The first thing is that the very first neuromorphic control paper was a paper about speed regulation, exactly like the paper of Maxwell on governors. And the second one is that if you want to understand, so far, neuromorphic engineering has not delivered. Why? Because this technology doesn't work. In the same way as the governors of Maxwell's time were not working. They were so complicated to design that people were giving up. And Maxwell showed that, okay, if you want to fix this, you need to develop a theory. You need to apply stability theory, and then you can make these systems work. I think we live in the time where we are going to fix neuromorphic technology by developing the stability theory of neuromorphic technology. And the stability theory of neuromorphic technology is a mixed feedback technology. So we are sort of connecting back to the vision of Wiener. Very quickly, this is the very first paper about showing the revolutionary aspect of neuromorphic control on speed regulation. The paper was published in 1991, 1 year after the paper of Carver-Mead. And Carver-Mead is one of the authors. Another author is Carl Åström, who is the big father of control theory of these days. And he was frequently visiting Caltech, so he must have heard of these new developments and got interested and said, why don't we put a student, Stefan de Weert, poor Stefan, and have him work on this. The paper has 38 citations today. So, flat signal. But I think there is a revolution in this paper. There is the gem of a revolution. Here is what they showed. They use a classical DC motor. And instead of controlling the DC motor with a classical PI controller, they replace the PI controller by an excitable spiking controller. And what they show is that when they regulate the motor at its nominal speed, it's the rate of, it's the spiking frequency that determines the torque. And that's nothing surprising for engineers, because most of speed regulation today is done with a technology of pulse width modulation. So this is exactly how motors are regulated today. But then they slow down the speed to a very, very slow speed. And if you would use this PWM technology, the motor would stop because of dry friction that you have not taken into account in your model. And instead, because of the excitable nature of the controller, the motor doesn't stop. The error builds up, and when it reaches threshold, you have one spike, and the motor gets a little kick. This is also a very well-known technology. It's called a stepper motor. Stepper motors are used for speed regulation at very, very low speed. You don't regulate the speed, you regulate the steps of the motor. What they showed in this paper, it is extremely simple minded way, form of intelligence, which is just sort of integrate and fire. The spiking nature of the controller sort of interpolates between those two worlds. Neuroscientists would call this a rate code, and they would call this a spike code. The debate in neuroscience as whether the brain uses a spike code or rate code goes to the present time, has been there for a century. When something goes for a century, it's probably that both are true. And what this technology shows is that neuromorphic has a sort of the potential of very smoothly interpolating between things that people consider completely separated today. Again, the discrete and the continuous, always there. As I said, I think it's a revolution yet to happen. I put 2028, maybe I'm optimistic, I don't know. We'll see. And I finish with the mixed feedback story. What is a spike? Remember the incredible concept of the cybernetics age, that one device can sweep, just depending on the tuning, between the analog world and the digital world. This is the connection that we have killed in the world, in the age of digital technology. What is a spike? A spike is exactly that. A spike, this is the simplest circuit that creates a spike. If you remove the inductive branch, you just have a flip-flop. You just have a switch. So the spike is a switch. But because of the inductive branch, as soon as the switch has occurred, the system repolarizes. So it is a switch in a very short time scale, and then it's regulation in a longer time scale. In other words, there is a mixed feedback principle behind the spikes and behind any form of spiking control intelligence. I'd like to finish with this picture of Horace Barlow, who passed away just a few months ago, I think. And we organized a workshop in 2016 on neuromorphic. And Orabalo made very nice recollections during the dinner of the Ratio Club. And it felt really sort of connecting back to the cybernetics age in a very moving way. With this, I would like to conclude, and I would like to conclude with 3 quotes or 3 remarks. The first one is that feedback theory is the science of hidden technology. This is a quote of Carl Aström that I mentioned earlier. As long as a system, as a control system works well, you don't see the control system. You don't know that there is a control inside. When something like Chernobyl happens, the people that are blamed are the control engineers. Okay, so control theory, every important development of control theory has arisen from a technological difficulty, from a device that was not working well. The speed regulator in the time of Maxwell, the mixed feedback amplifier in the time of Wiener, and the neuromorphic circuit today. The second thing is that I find this quite remarkable, and we have seen that throughout the day, how Maxwell was, even though he was he had a great theoretical mind, but was very interested in building actual devices. And maybe the most theoretical physicist of the 20th century is Richard Feynman, who said, "What I cannot build, I do not understand." And I feel so much in the sort of the heritage of Maxwell by thinking that we will not understand the brain until we build intelligent machines. And the last thing is that I really think control theory today as the science that will reconcile physics and algorithmics. And I think that the gap between physics and algorithmics is one of the most one of the most pressing issues of the current hype of artificial intelligence, but that the type of intelligence that we have so successfully developed is extremely virtual and is extremely difficult to connect back to the physical world. And I think that we see that also in the paper of Maxwell, the fact that he took an extremely concrete physical machine. You could say that the speed regulation, the watt regulator, is a physical form of intelligence because you connect a physical device to another physical device. But then he sort of pointed out to the importance of a theory to help the design. Perhaps today we need to go the other way around, but this dialogue between physics and, at the time, mathematics, today algorithmics, I think is extremely important and somehow is something that is forced upon control engineers. And for these reasons, I think that it's really legitimate to call Maxwell the father of control theory. Thank you.